Hello and welcome. In this video, we're going to look at how to calculate the total inductance in this series parallel combination circuit. From the top here, we have no choice but to enter into a node, and so we'll see that something's in parallel right there. We see that that parallel leads us through L1 and L2 before we hit a new node, and we can even call this node node A. Right? And so since we have no choice but to go through both of those two inductors to get to node A, we're going to sum them together. We're going to say that they're in series with each other. So we have L1 in series with L2, right? And we know that that's in parallel with something to get to node A because we have two pathways to get to node A specifically. We can go from L1 and L2 branch, or we can go down the L3 branch, which means that L3 is in parallel with the series of L2 and L1. And so we'll make sure that those two are put into a series parallel combination. Right? So we'll say that this is in parallel with L3. We want to make sure we do all of this combination here, innermost parenthesis first. So add L1 and L2 together and then put that number in parallel with L3. Okay, so now we have our node A location, and node A, everything kind of has to go through node A. So whatever's on top of the circuit, whatever's at this top half here, must be in series with whatever's at the bottom half down here. Right? That's because that node A has everything traveling through it. It all kind of combines into one singular node. So we'll keep going with that, and we'll represent node A as a plus, right? Because it's in series with whatever on the bottom half here. So plus, and that's our node A location. And we'll move on from there and say that from node A, we can go across L4 to get to our ground location, or we can go across L5 to get to our ground location. And that means that those two are in parallel with each other. So we'll open a parenthesis and we'll say L4 is in parallel with L5. Okay. So we can add these up and put them in the series parallel combinations. We can technically even do it all in one go if we wanted to, but we got to watch out for our micro versus millihenries here. So we see that L3 here is a millihenry or microhenry value that we can move into millihenries. So we'll move it forward 1, 2, 3 locations and say that it's actually 1.1 millihenries for L3. We can do the same thing for L2. It's in micro, so we'll move it forward 3, 1, 2, 3 here, put the decimal point out front. We have 0.45 millihenries. And so now they're all in millihenries, and we can put them all into one equation. So now we'll open two parentheses. We'll open a parenthesis here and do our 1 over 1 over equation. So 1 over 1 over. And in the first part, we want to make sure we add L1 and L2 first. So we'll put both of those on the bottom of this parallel here. We'll say that we have 1 millihenry plus 0.45 millihenries, right? That's the series combo of L1 and L2. And we'll put that in parallel by saying plus 1 over the L3 value of 1.1 millihenries. Okay, and that closes off our orange parenthesis there, ending the first top half of our circuit. Now we're at node A, so we'll add the bottom half of our parallel resistance here. We'll say that that is L1 in, or L4 in parallel with L5, so we'll say that is 1 over 1 over L4, 2.4, in parallel with, so plus 1 over 2.4. And that gives us our total series parallel inductance for this circuit here. So we can say that our LT is equal to 1.82 millihenries. All right, let us know if you have any other questions.